All right. We are going to get into the ones where we do definite area underneath a curve or a geometric shape looking thing. And we're also going to get into hopefully the second fundamental theorem today. Those are my goals. Okay, so my goal is to try to get these finished today. And then tomorrow, hopefully, will be some kind of review, probably with a quiz. Monday is what we're looking at over this new stuff. I know I owe you some grades from some old quizzes. I'm hoping to get that caught up over the weekend, and we'll be back in business. Okay. And again, out of Unit 6, we're going to do like one more thing, and then we're going to be done with Unit 6. So we're trying to move as quick as we can. And I may take 7 and 8 out of order, depending upon where we're landing on time, because I don't know. We'll see. I don't think I'm going to be able to get far enough where I want to be by Pi Day, so I might just leave it. Come up with a different activity. All right, so pictured below is the graph of a function f. Find the values of each of the following definite integrals. If the value does not exist, explain why. Okay, so I'm going to zoom out so we can kind of see it all at one time. So we're going to use that graph significantly. A College Board loves to do one of the parts of the question is find the definite integral, and then the other part is determine where it's increasing, decreasing, concave up, concave down. So they love using this picture and putting a couple of these different concepts together. The fact that we hadn't been able to integrate yet meant I couldn't show you a full Fourier response question. Okay. In a couple of weeks, we're going to see a full Fourier response question. And you're going to see we have to go back and forth between derivatives and integrals within the Fourier response question. Okay. All right. So the first thing, I'm going to keep marking up my picture a whole bunch of times. Okay, so I'm going to kind of mark it and erase it and mark it and erase it, okay, over and over. It really helps when you can scribble on there. And again, on the AP test, it's pencil paper, so you can scribble on your picture as much as you want. Okay. All right, so it's saying that we're supposed to be going from -4 to 2. So I'm going to draw that on my graph. So from -4 to 2. So we're going to use the geometric, because all we know is that graph. So all I got to do is I'm going to use the geometric shapes that are there to find the areas of the shapes, and I'm going to add those areas up. Okay. What shape is this first one right here? It's a trapezoid. Okay, so we're going to find the area of that trapezoid. We know we have to add our bases together, multiply by the height, and divide by 2. My bases are... Actually, that's not a trapezoid, is it? We don't have 2 parallel sides. Can't be a trapezoid, right? Looks like we're going to have to break it up just a little bit more, right? Because trapezoid needs 2 parallel sides. I don't see 2 parallel sides. So I'm going to break that one up a little bit more. I know I need both of them. I could do a trapezoid here, right? With this triangle there. Does that make sense? So I could use that. I could do that one, and that one, and add those areas together. So now I've got a trapezoid. What are the lengths of the bases here? So this is base 1, that's base 2. What are those heights? How big is this one? How far did it go down? 3, good. And then what's this one right here? 2. Okay, and then how many is it? Technically, the height of the trapezoid is kind of what we've been using, is distance in between. So how big is that? 3. Okay, good. So if I just keep calculating the trapezoid, I'm seeing 5 times 3 over 2, or 15 over 2. I'm going to add that to the next piece. All right, the next piece is this little tiny triangle in there. So what's the base of the triangle? 1. Height of the triangle? 2, and it divided by... Now there's something I didn't take into account on both of these that I have a mistake on it right now. Are those shapes above the x-axis or below the x-axis? What do we know about things that are below the x-axis? They're negative, so I need to put a negative on this. And then I need to put a negative on this one as well. I should have had the negative up here the whole time. Okay. All right. I could reduce this if I wanted. I may have to scale it back up later, so I'm going to reduce it to -1 for now. Okay. All right. Finally, we have the area of this triangle right here. What's the base of that triangle? 2. Okay. So base is 2. Height is 2. Okay, so that reduces to, it looks like we're just going to get a 2. It gets to be positive. I'm going to erase this and put it together. So what's negative 1 plus 2? 1, which if we want to go back into common denominators, we'd use 2 over 2. So negative 13 halves would be my final answer on that one.
What is the second one be?
Oh, we know.
No, I'm stupid.
You're not stupid. Okay, don't call yourself stupid. You made a mistake, right? That's okay. All right. No one in this room is stupid. You all took AP Calculus. You were smart to do that. Okay, let's look at the next one. All right, kind of more of the same. All right, so I'm going to erase my picture because I'm going to scribble all over it again. Okay. All right, this time it says I'm going from 0 to 3. So I'm going from here to here. So what shapes do we see in our picture this time? What shape is this right here? Triangle. What shape is this one right here? Another triangle. Okay, so I got to do base times height divided by 2, right? What was the base of this triangle? 2. What's the height of that triangle? 2. All right, base of this triangle. 1, right? And then what was the height of it? 2. And then what's special about the area of that one? What am I going to have to take into account? It's negative. Good. All right, so it looks like, and I'm going to purposely leave it in halves because I'm seeing what's coming in that second one. So I might want to, actually, no, I don't need to leave it in halves, do I? It can reduce. Never mind. So 2 goes into 2 twice, so I've got that. I get 2 minus 1, which is 1. Okay. All right. Let's try another one again. I'm going to erase my scribbles. All right. This time it says that I am supposed to be going from negative 1 to 1. So I'm going from here to here. We kind of talked something about this. I think it was 2 days ago. Okay. We'll see it again here in properties in just a moment. All right. So what kind of shapes do I have? Triangles. Okay. So I know I've got to do base times height divided by 2. All right. What's the base of this first triangle? What's the height? Okay. What's special about it? It's negative. So I got to make it negative. All right. So that's going to give me, it looks like negative 1. All right, second triangle, what's the base? Okay, what's the height? 2. It's positive, right, because it's above, so it looks like 1. What's my overall area? Ends up being 0, right? It should make sense because if we look at those triangles, they're the same triangle and one's above and one's below, so it's going to zero it out. Okay. All right, let's look at D. All right, so D says we're supposed to go from 0 to negative 4. Okay, so I'm going from 0 to negative 4. What on earth? How come it worked on my end? Negative 4. I'm looking at what I wrote last year, and I don't necessarily agree with it. It's not continuous if x equals negative 1. So that wouldn't be on all of them like that. Okay. So let's see what kind. We're going to have to break up that shape. We kind of did this one already, didn't we? We did it kind of in the first one. So what is the, whatchamacallit? So I have what 2 shapes there again? What's this first shape? Trapezoid. What's the second shape right there? Triangle. Okay, so I'm going to do the area of the trapezoid plus the area of the triangle. So I know I'm going to divide them both by 2. All right, what is the first base of my trapezoid? How tall was this? 3, right? Well, how was the height of this part of the trapezoid? 2, good. And my base of my trapezoid, or my height, actually my height of my trapezoid? 3, okay, good. And then my triangle, it looks like 1 and 2, right? And then what's special about both of them this time? They're both negative, so I got to make them both negative. All right, it looks like we have negative 15 halves minus 2 halves. So it gives us negative 17 halves. Okay. Oh, I see what's different. Okay. We're going to take something off of this one because I totally just neglected it, but I'm not going to redo the problem. Scribble out the f prime on that. Okay. Because I made a mistake there. I see what I did wrong now. So we're just going to pretend it was that. It was f. Okay. Do you see how these ones were all f? And do you notice how E and F say f prime on it? Okay. So I should have done D a little differently than I did. I now understand what I did wrong on D, but I'm not going to go back. Okay. So when I integrate f prime, what should I get back to? We talked about that yesterday. We should get back to f, right? So it should be f of x. Excuse me. Oh, baby. Oh, excuse me. All right. So it should look like that, right? Because because I had the f prime instead of the f. So now it looks kind of like what we did yesterday, and I'm going to substitute in the 1 minus f of negative 1. Now we have f, which is our graph, and I'm going to go read those values off the graph. Okay, so let's go back to the graph and let's find f of 1. Remember, this is like reading the y value. We've done this a whole bunch of times this year. So f of 1 is what? 2. What was f of negative 1? Negative 2. So 2 minus negative 2 is going to be 4. Okay. F is very similar to what we just did. So I want you to try f. So integrate it, plug your numbers in, go read your y values off the graph. Give you a minute to do that. All right, what'd you get for f of 3? Good. And then f of 1? 2, so negative 4. Okay. All right. We're going to go ahead and we're going to go over the properties, okay, of definite integrals. So these are things that when they come up, we should just really know them. And there's some nice shortcuts in there. Like one or two of these problems that we just did, we could have done by this shortcut, okay, and not had to do the actual problem. So what really is happening in number 1 is that when I am integrating to and from the same variable or the same number, so I'm going from 1 to 1, or I'm going from 2 to 2, okay? When I would subtract that means when I take the antiderivative, it would be the same antiderivative evaluated at the same number, it should be 0. So when I see a number to itself, I know my answer is always 0, okay? We are allowed, one of the other properties we're allowed to do is we are allowed to break an integral up into 2 different parts. So if there is an x value that's between our 2 bounds, we are allowed to break it into two separate integrals. Sometimes that helps us integrate it easier if we're having trouble integrating it. Okay, I want you to look very, very carefully at number 3. This one comes up quite a bit. What's the difference between the integral here and the integral there? Okay, the a and the b are switched, right? We always want b to be bigger. All right, we want this one to be the larger, we always want that one to be larger, okay? If it's not, and this is the context that we typically use this in, so we want that to be larger. If it's not larger, we swap the order, and when you swap the order, whatever the value it's equal to becomes negative, or we make the outside of the integral negative sometimes. Okay, so when you swap the order, you get a negative. Let's look at what the next one is. Oh, what I just explained is what they're talking about here. Given that b is less than a, so if I have that b is smaller than a, I'm going to make it negative out front and swap the order. We just talked about that. So same property, kind of just stated a different way. All right. On number 5, we talked a little bit about this yesterday. We started using it yesterday. If we have a constant times a function, we are allowed to take that constant and bring it in front of the integral. And sometimes it helps us see the integral better. Sometimes it gets it out of the way so we aren't dealing with that coefficient. All right. Like many of our other properties that we have for like logarithms and other things that we've got, when you're adding and subtracting integrations, you can split them up and add and subtract them separately. Notice I'm not changing my interval at all. I'm not changing my bounds on there. I'm just splitting it up into 2 because sometimes it's easier to do them separately. Okay. This isn't a property I use a whole lot, but if you see it and you recognize it, great, use it. If you don't, you're going to be able to do the integration the way we've been doing it, and you'll still get the right answer, okay? If you happen to recognize that you have an even function, okay? Remember, an even function, if you're looking at it, will have y-axis symmetry, okay? If I think about, let's say I'm integrating from here to here, and it's the same value. So this is a, and this is negative a. I did not draw a very even picture there, okay? But shouldn't the area here and the area here be the same? They're the same distance out from 0, just one positive, one negative. So if they're the same, I could integrate just from 0 to a of the function and double it. Or I could double integrating from negative a to 0 of the function. Again, if you don't remember that one, it's not going to hurt you. It's just, if you know it, it's a shortcut. But you can still integrate from negative a to a, plug the numbers in, and you're going to be fine. Okay. Okay. An odd function, just as a reminder, has origin symmetry. That says origin symmetry. It does not look very good. It doesn't even look like 2 words. Origin symmetry. Meaning if I twisted it around the origin, it's going to land on top of itself. Okay, we actually did one like this a few minutes ago where it had this origin symmetry to it. So if this is negative a and this is a, think about this. This area and this area look the same, except one's positive, one's negative. They would cancel each other out, so it equals 0. So if you have the same number but opposite signs, the answer is always going to be 0. And you do not have to do any work. You just write a 0. Okay? Okay. So those are our properties. We're going to apply our properties. You can use them really in anything. They might give you a table, they might give you a graph. Sometimes they like to just give you some couple of integrals and some values, and then we have to apply the properties. This is really common way that they assess this. So go ahead, and I just want you to take a minute, read that to yourself. Okay. Okay, so they gave us two integrals. They told us that from 0 to 3 of f of x dx equals 6, and from 7 to 3 of f of x dx equals negative 8. Okay. We're going to use our definite integral properties, and then for the explain how you arrived at each answer, just you're showing your work. Okay. So when we just talked about this a few minutes ago, do we like the look of this thing right here? Do we like that bigger number on the bottom? No. So how do I fix that? Yep. And then what do I do with the bounds? Flip them. Good. Okay. Now that I have it fixed, because it really bothered me, right? What I am looking at is I notice that 0 to 3 of f of x dx is the same as that. And if that's equal to 6, can't I just substitute 6 in for it? So on this one, I'm just going to get negative 6. The negative comes from us doing the flip. Okay. All right. All I know is I've got something from 0 to 3 and I've got something from 3 to 7. Okay, they want me to go all the way from 0 to 7. But remember we said we could split it up somewhere. That was one of our properties. So I know that if I go from 0 to 3 and I add that to 3 to 7, it should be the same thing as going from 0 to 7. So all I'm going to do on this one is take the values of the two integrals and add them together. So we've got 6, and then for the first one, and then we're substituting in negative 8 for the second one. So overall, we get negative 2. Okay, let's keep going. When I go from a value to itself, what's the answer? What did it say up here? A value to itself. 0. No work, right? Easy peasy. Ooh. 0. Okay, this one has a lot of things going on. Okay. First thing I would do is I would probably take that 3 and pull it out front. Okay. What else do we not like about the look of that? Bigger numbers on the bottom. How do we fix it? Yep, and then swap the values of the bounds. All right, I am looking for the value of the integral of 7, or from 3 to 7 of f of x dx. What is it? Go back to the stem and read it. So negative 8. And then multiply negative 3 times negative 8. Hopefully we get 24. Okay. Looking at E. All right. I am going to I'm actually going to split it into two different integrals. Remember how we can, when we're adding some things together, sometimes sometimes it makes more sense to split it up. So I'm going to use that property. So 3 to 7 of 2 dx plus, at the same time I'm splitting this up, I'm going to move that 3 out in front, from 3 to 7 of f of x dx. All right, this one has a little bit more work to it than the last few we've done. 2dx is not one of the things where you're just assigned and can sub in for. So we're actually going to integrate that part. So when I integrate 2, what do we get? 2x, and we're going to evaluate that from 3 to 7. I'm going to go ahead and just continue that. So that means I've got 2 times 7 minus 2 times 3. What's 2 times 7? Good. And 2 times 3? Good. And then we're going to add that to whatever we get with this back piece. Okay, what are we substituting in for the integral from 3 to 7 of f of x dx? Good. All right, so that gives me negative 24. And hopefully when we add it all together, negative 16. Double check my arithmetic. Okay. In letter F there, they're telling us that the function is even. Remember, this property only works if it's even. So if it's even, I know I can go I can double from 0 to 3 of f of x dx, which is information that we have. So that would be a reason to actually use it in this manner, because I don't know anything from negative 3 to 0. So what did they tell us it is from 0 to 3? 6. So we're going to get 12. Okay, it's the same in G, except they switched it to the word odd. If it's an odd function, when I go from negative to a positive of the same number, what's the value? 0. And I didn't even have to give you 3s, right? I could have given you 4s. I could have given you 6s. Doesn't matter. It's always 0. All right. We get out at 16. All right, we still got plenty of time. We're going to keep going. See if we can get through a few more of these. I'm not sure we'll get to where I wanted to get to. Okay. The graph pictured is f of x. We need to find the value from 0 to 3. Okay, we might start some of these together, and I might have you try a couple on your own. So I'm going to go from 0 all the way to 3. All right, I see all kinds of weird shapes in there. And again, College Board loves these. So we're going to make sure we know how to do them. I'm going to draw some extra lines in there. So I'm going to draw that in there. Ooh, I'm going to draw that in there, and I'm going to draw that in there. I could have probably left it as a trapezoid, but if you want to do rectangle and triangle, that's fine. All right. Do you see how this here, it's part of a circle. How much of a circle is it? 1/4 of a circle. All right, so let's write that out. So we're saying we're going to integrate from 0 to 3 of f of x dx. I am starting with a quarter circle. What's the formula for area of a circle? Well, what's in it for sure if it's a circle? Pi, okay. There you go, r squared. When Ellie was in 6th grade, I told her when she was doing area of a circle, I'm like, tell your teacher pi aren't squared, they're round. So every time they did area of a circle, she'd raise her hand and say, Miss Ellis, the pi aren't squared, they're round. So anyways, that was the bad math joke of the day. All right, we're going to divide that by 4. But really, I don't want r. What do I want to put in place of r? What's the radius of this thing? 2. Good. Okay. All right. I've got a rectangle and a triangle. So my rectangle, what's the base of the rectangle? 2. What's the height of the rectangle? 1. All right, and then my little triangle there, what's the base? 1. Height? 1. So 1 times 1 over 2. Okay. It looks like I'm going to need to be in halves, doesn't it? Because this isn't going to reduce. So eventually I'm going to have to come back to halves. What's 2 squared? 4. Can't these just cancel? So I've got pi plus 2 plus 1/2. There's a number of ways you could do this from here. You could make this 2 pi over 2 plus 4 over 2 plus 1 over 2. And then it would be 2 pi plus 5 over 2. why did I, yeah, okay. I totally wrote the wrong number last year. We could also have left it as just pi plus 5/2 and not done the scaling this part up. Both of those are fine. Okay. All right, let's see what they give us next. Sometimes it's good to know what they actually are. Let's see what I'm going to do with that next one. Okay. So sometimes what I'll do when we're given the same picture over and over and over is instead of calculating the area 5 million times, we know that this area here calculated to pi, right? We know that this chunk right here calculated to 2, and we know that that one right there is 1/2. Okay. So rather than doing the calculation over and over and over, sometimes I'll do the calculation at the beginning, and then I just mark in there what it is, and then I can just add them up. Okay, when I get to whatever I need to get to for the next one. All right, this time it says I'm going from 0 all the way to 4. Okay, it looks like I've kind of got the same parts again. I know this one was pi, this one was 2, this one was 1/2, right? That one's 1/2. What do you notice about this triangle and that triangle? They're the same. So what's the area of this one going to be, though? Good. So what's going to happen with the 1/2 and the negative 1/2? They're going to cancel. Good. So we've got from 0 to 4 of f of x dx equals, we're going to add up pi plus 2 plus 1/2 minus 1/2. So you're going to get pi plus 2 or 2 plus pi. Okay. Let's take a look at the next part. All right, the next one says we're going to go from -3 to 3. Could I use some of the information that I already have? What's this little quarter circle? What did we say it was? Pi. Good. What is the rectangle? 2. And what's this little chunk here? 1/2. Could I just take what I had before from 0 to 3 and just double it? Yeah, I could do that. Or I could add up pi plus 2 plus 2 plus 1/2 plus 1/2. Your choice. Okay, let's go with the doubling thing since that's what we were kind of talking about today. Was one of our properties. So we're going to write from -3 to 3 of f of x dx. We know that that's the same as going doubling from 0 to 3 of f of x dx. All right. We already know this value, don't we? Didn't we do it in part A? So couldn't I just kind of cheat and steal it from part A? I'm just going to take that and multiply it by 2. So 2 times, it was 2 pi plus 5 over 2. So what happens with these 2's? Cancel. So we just get 2 pi plus 5. Maybe. There we go. Okay. The next one has a weird thing happen here. All right, my goal now is to try to get us maybe to example 11. Okay, we'll see how it goes because I don't think we're going to finish. And that's a good cutoff point. We'll do second derivative or whatever it is, second fundamental theorem tomorrow. All right, so notice it's actually, just read that to yourself first. Read it once to yourself. Okay, I think we did start talking about this when we did some of our rate problems or our position velocity acceleration. I think we talked about an initial condition, right? This thing here, whenever you see 0, f of 0 equals something, that's what we call an initial condition. That means that's where this y value is starting. So they want me to find the f of 3, right? The anti, which is where f is the antiderivative of f of x. So basically I have to integrate, okay? So I am going to find, I'm going to start with this y value 5, and I'm going to add it to the integral of f of x. It says, though, that's the ending value of x. This is the beginning value of x dx. So let me explain that one more time. I write it down and I'll explain it again. Okay, so again, we know how to do it. It's the way the problem is being stated. It's stated a little differently than we were stating them before. Okay, it gave us this initial condition. The initial condition gives us two things. It gives us a y value where we're starting, so I have to start with that in the y value. Okay, it also gives us the first x value that's our lower bound, and that's always going to be our lower bound, even if it's a bigger number. Okay, then it's saying, hey, we're going to go all the way until we hit the x value of 3. So that's how I got that upper number. It said it was the antiderivative of f of x, which means I have to integrate f of x to get there. Okay. Do we already know what this value is? Have we done that like a million times on this problem? Was that the answer to the first one? Yeah? No? Yeah? 2 plus 5, 2 pi plus 5 over 2. We're just going to leave it like that. We're going to pretend it's free response and leave it like that. Okay? If we really wanted to, we could make it whatever, 10 fifths or 10 halves and add it together. Okay. Let's do the same thing on E. E is going to have another slightly different piece to it, okay? All right. Read E to yourself. Okay, what do we call that part that f of negative 2 equals 2? Even though it didn't say 0. What do we call it? That's your initial condition. That means when I integrate, I'm starting with a value of negative 2. The bottom x value of my integral also happens to be negative 2. Okay. What is going to be the value of this upper bound of my integral? It's going to be 2, right? We're getting it from right here. Okay, and then it's of f of x dx. All right. I am going to go back, and now that's a totally new set of values on my picture, right? Though I could cheat a little bit. I know some of these values, don't I? What is this value of the quarter circle? Pi, good. All right, what was the value of the rectangle? 2. And I could double it, couldn't I? Yeah, might as well use the property. So we're going to go from 0 to 2 of f of x dx. So I've got negative 2 plus 2. And we're going to add pi plus 2 to it. Again, I could probably leave it. I could probably get away with it. I'm going to simplify this time. So 2 pi plus 2. Okay. 10 and 11 come like directly out of what are their delta math problems. I can tell just by looking at the font and the format of the graphs there. So a little bit different, but very similar to what we've been doing. We're going to actually change the areas up on us this time. Okay, so take a minute and just read that, the instructions are to yourself. Okay, where am I starting my integration? What value? What's it tell us? It's my lower bound. Negative 8. What's my upper bound? 9. So I've got to do all three of those shapes. Okay. What is this first shape? Triangle. Okay, so let's find the area of the triangle. What's the base of that triangle? 8. Good. What's the height of the triangle? 4. Okay, and we divide it by 2. Okay. What shape is this second piece? Is it a whole circle? How much is a circle? Half circle. They'll never give you, I take that back. When we get, because we're doing some area right now, we eventually get to volume. We have whole circles in volume, but they never in this type of picture are going to give you a whole circle. It will either be a half circle or a quarter circle. Okay. They won't do anything weird like an eighth of a circle or something like that. Okay. It'll be something obvious, half or a quarter. All right. What's the radius length of this circle? 3. Okay. So pi, what's the radius? What's 3 squared? 9. I could have written that as 9 pi. I didn't have to write it in that order. All right. Finally, what shape is this down here? Triangle. What is special about it? Negative area. Okay, now I'm going to divide by 2. Let's see. 1, 2, 3. Make sure I counted right. What's the height of it? 6. Good. Now it's all arithmetic. Okay. Now look at, before you just start wildly crossing stuff out. Okay. I would look at my answer choices. If they had a 2 in the denominator, because look at your middle term. Your middle term is going to stay over a fraction, right? If my answer choices had it all in fraction, I would leave it the halves. If they didn't, I would go ahead and cross out. Okay, so let's leave it in halves for right now. Okay, so let's see. What's 8 times 4? 32 halves plus 9 pi over 2 minus 18 halves. Do we agree? Did I multiply right? All right, so what's 32 minus 18? 14. So 14 plus 9 pi over 2? All right, we've got just enough time for one more. Okay, here's what I want you to do. I want you to give example 11 an attempt on your own. Okay, see if you can figure out what shapes. There is a little bit of a catch. Okay, so I'm going to give you about 2 minutes to see what you can do with it. Okay, at least try to get the obvious shapes. There's one in there that's weird. Okay, 2 minutes on your own. Try it. Make sure you really watch where you're going to and from. About another 30, 40 seconds on your own. See what you can do with it. Of course. Okay, look at what I've done so far. Yeah. All right. So I want you to take a look. Do you see what's going on with the triangles, the pink and the purple triangle? They're the same, opposite. What's going to have? What value do they have? They're 0 together, right? They're going to cancel each other out. Okay. Did you notice that it didn't go the entire length of the graph? That it stopped here. Okay, so it said stop at 4. So you got to watch for that. You got to read. Okay, make sure you're stopping, because if you went all the way to 8, you added an extra rectangle in, right? Okay, here's the part that was a little bit tricky. Do you see what I did in orange there? Do you see how it looks like a graham cracker? This is why I'm thinking about this. It looks like a graham cracker that I'm going to give to my youngest, Davy, right? And then Davy comes in and takes a big bite out of the graham cracker. This is what they want the area of right there, is that funky looking shape there. So it's a rectangle minus the bite from Davy, the semicircle. Does that make sense? Okay. I know you've seen stuff like that in geometry. It's just been it might have even been like 7th, 8th grade geometry since you've seen something like that. Okay. So I'm going to do the orange rectangle, which I think was an 8 by 7, if I calculated right. Okay. And then the semicircle, I'm going to, and it should also be what? Because it's underneath, what should it be? Negative. Okay. So it's going to be negative. Actually, it's going to be really weird. Let's see. How did I write it before? Yeah. Okay. It's going to be negative. And then because I'm taking the bite out, I have to subtract, right? Because it's going to be all kinds of sign issues right here. Then I'm going to I know that bite area is also negative. And then I got to do the semicircle. Pi, the radius length is 4, so 16 divided by 2. Super weird. Okay, the double negative is going to go positive. I know those are going to cancel, so I get negative 56 plus 8 pi. Okay. All right, we will do second fundamental theorem tomorrow. What I'm going to do is on the homework, I right now have a worksheet up there for second fundamental theorem. I'll just move that to tomorrow, but you should be able to start working on homework, okay? So don't skip it tonight. Start working on it so you make sure you're practicing this stuff. This is going to bump. Instead of doing a quiz on Monday, it'll probably be more like Tuesday. I'm sorry. I know you were all looking forward to a Monday quiz, right? You all wanted it on Monday. Fourth period was lobbying for Tuesday. They'll be excited.